Sorry. So, program button. Find dist fill for starters. Dist fill. Third one on mine. That's all. Oh, maybe Jeff has stuff in there. Just press enter and then press enter to start it. And then what it's going to ask you to do is it's going to ask you to build the distribution with it. So you have to know before you start what your x values go to. So that's why I wrote the program like this. It doesn't do everything for you. It does the annoying part for you. So you still have to know how to, so you have to know that you're dealing with chickens. The distribution from yesterday was chickens. And if we're talking about the number of girls per flock of size 4, the least number you can have is 0 and the highest you can have is 4. So you're going to put in 0 for smallest, then press enter, and then 4 for largest, and then press enter. Now at this point, were you to stop the program, I will do this, you don't. You guys just sit tight for a second. Right now, if we stop the program and look, L1 is filled with 0 through 4. And whatever you had in your list is gone. Sorry if you wanted it. And it's filled from 0 to 4 in list 1. So you're that far. It will now fill list 2 with the probabilities that you tell it to. So, let's go back to that, start it again. 0 to 4. You have to tell it what distribution you want to put in list 2. Now, I would guess 100% of the time you guys are always going to use this for the binomial. I also put in other ones, uniform, PDF, and manual. Don't worry about any of those right now. You might never use those again. I was building the program more for a macro view than a micro view. Most students I found just use the binomial. So generally you're just going to be pressing enter right now. And then it asks for that one beautiful probability that you need to know to do the binomial. And the probability. What was the one probability we used all day Tuesday? 90% of the birds are girls, 0.9. And it's got to be a decimal. It's got to be a number that gets pissed. So 0.9, it will. It'll give you a nice little error, kick you out. Okay? Actually, it might not. Yes, it will, because the binomial command's in there. Press enter. It's going to think for a couple seconds, then say done. Now go back and look at your lists. That. Edit. Those numbers should look familiar to you. Those are the numbers we did in class. It was the last distribution we did in class. There is basically a 1 in 10,000 chance you're going to get all roosters or no girls. There's about 0.4% chance you're going to get 1 girl and 3 boys. There's about a 5% chance you're going to get 2 of each. These I would call the weird cases. They don't happen very often. Do you have a right to be pissed if you buy 4 birds from the store, bring them home, and of the 4 of them, 1 of them grows up and becomes a rooster?
No.
Do you have a mathematical right to be pissed? No, because that's going to happen about 30% of the time. Sure, it's more usual, roughly 2/3 of the time. Roughly 2/3 of the time you're going to get all girls. But that means 1/3 of the time, as you might recall from my discussion with the guy in High Desert, roughly 1/3 of the time you're going to get a boy in there somewhere. Chances are you're not going to get more than 1 boy, but you're going to get 1 boy roughly 30% of the time. This is the important part of that distribution, being able to look at those numbers and do the analysis like I just did. Where are the unusual cases? Where are the usual cases? These guys are huge. He's technically borderline if you go by statistical exactness. Most journals nowadays use 5% as a cutoff for something that's unusual. A couple of you are nodding, you've seen this in psych journals and social journals and HDPS journals and exercise science journals. Any p-value, or probability value, more or less than 244, below 5% is triggered as unusual. So this is technically less than 5%. I mean, it's technically, but it's damn close at that point. These are the ones that are truly, truly weird, less than 1% of the time. And these are truly, truly not weird. If you add those 2 together, you get essentially 95%. Which correlates nicely, even though this isn't the bell shape, that correlates nicely to the normal, if you will. Not normal in the bell shape, but the usual, what's going to usually happen. Most of the probability happens around 3 or 4. So most of the time you're not going to get more than 1 rooster. 2/3 of the time you're not going to get any. That's where this is useful, to have those numbers in front of you and talk about them intelligently. Not the calculation of them. It's fun. It's mathematically beautiful. If I have time, I'm going to make a video showing you the mathematical calculation out for the general case. I won't have time anytime soon, unfortunately. But I want to, it's on the list of things to do is to walk through a manual. manual, general calculation, in case you need it. It's just not there yet. Now the beauty of this, going back not quite as extreme as 2 million, Carly's case of 2 million, I had a student in the other 243 class is going to have a flock of 41 chickens. 41 chickens. This can handle that like that. Think about it, we'd have to have 41 pictures of chickens on the board and be able to analyze, okay, how many ways can you have one boy and 40 girls? Well, there's 41 potential. How about 2 girls and 39 boys? Well, that's I think about 600 or something like that, different ways. Alice is shaking her head, no! No is right, no! So go back, program. Run it again. Run it again. Disfill. Smallest value, she has 41 birds. What's the least number of girls she can have?
0.
0. What's the most number of girls she can have? 41. Hit enter. It's going to take a couple seconds longer to fill that in. Binomial again. What's the chance of a girl?
0.9.
0.9. We're still making that independence assumption. Hit enter, let it think for a few seconds. It's filling in list 2 as we speak. It takes a little bit of time because it's going through. It's called a logical if loop right now. It's doing the first one, then doing the second one, then the third one. It's done. Let's take a look. Stat edit. Okay, so we're going to feel pretty good.
Wow.
That we're not going to get all roosters. That's essentially 0. These are all essentially 0, aren't they? I mean, if you think about it, these are all zeros. Mathematically or logically 0. Start scrolling down until you start getting some measurable probabilities. Where does that start to happen?
About 30, 31.
30, 31. Love it. There we go. 30, we're at 0.1%. So I would still not expect, what would that be? 11 boys and 30 girls, right? I still wouldn't expect that many boys. Now we're at about 0.5%. Still pretty unlikely. 1.2%. About 3%. Now we're getting into the stuff that's actually, if you will, measurable statistically. This is above 5% now. 6% is still pretty small. Where are the big ones? What's the most common outcome?
37.
There it is right there. We just went right by it. 21% of the time, which is not a sizable chunk, right? That's 1 out of 5-ish. 20% is 1 out of 5. So if I send her to the store 5 times to buy 41 birds each time, in one of those 5, she can expect 37 girls and the other 4 boys. Does that make sense?
Yeah.
So that's the mode. That's the mode. The average, I'm guessing, is going to be a little bit below. We can calculate the average momentarily. We can do that pretty simply, actually. We'll come back to that. Then it starts tailing off. Look. What's the chance of getting all girls? Very unlikely. Explain that to me. How the hell was that the most likely case for us? And now it's very unlikely to get all girls for this flock of 41.
Numbers.
Give me more than the numbers. I love that, Pat.
As you,
No, go ahead.
Go ahead.
She's going to say the same thing.
She's going to say the same thing? Okay. You guys are fused. Go ahead, Riley.
because as you add more, you decrease the likelihood of having all girls, or you increase the probability of getting a boy.
Yeah.
It's because of the numbers. Think about it. Every time, these little fuzzy things are dice. They are a 10-sided die, right? They are a 10-sided die. 9 of the sides have G's on them, and 1 of the sides has a little B on it for boy. That's what 90% means, right? So every time Max goes in the store and grabs a bird, it's like me back there rolling a die. Okay, that one's gonna lay eggs. Okay, that one's gonna lay eggs. Just like in Vegas, your luck is gonna run out eventually. Because it's not luck, it's probability. There's nothing luck about it. So, what does the 90% chance of a girl mean again? Remind me what that means again?
It means that 9 times out of 10, you're gonna get a girl.
And give me 2 more words. Oh, I'll accept either of those 2 words, on average or over time. So, 41 birds is a sizable chunk of time, time being the number of birds bought. So on average, there should be, if you think about it, out of every 10 birds she buys, 1 of them should be a boy.
Right.
If she buys 41 birds, she should have about 4 boys, and she should have the other 40 be girls. Does that make sense?
And that's why 37 is the highest number.
Because it's the average isn't exactly 37, but it's damn close to it. The 0.1 screws it up a little bit. But that's why you're split. FYI, a second program I gave you guys in here is called Dist Draw. You might want to run that one right now. This gets a little tricky to see because there's so many in it. But if you run Dist Draw along with Dist Fill, you get a graph of the distribution, and you can get a visible spike at where the mode and pretty much the average are. Do you see that?
Yeah.
Here is 0 through essentially, I think, 32. There's, I think it was 37, right, Pat? There was 37, 36. Now, if you need the numbers, just press trace and scooch. So if you press trace, you can scooch right along and find them. But there's your chance of 0 girls, chance of 1 girl, chance of 2. Yeah, it's going up. It's going up. It's getting less 0. Still 0 enough to be 0, though, in my opinion. Okay, this is not going to happen. If stuff like this is happening, if you buy 41 birds and only get 14 girls, what's up?
They screwed up.
That 90% is probably wrong. There should be some other percentage besides 90 that's not 90, much lower. So now we're over here, we're over here, we're over here, we're over here, and then we finally get into the part of the curve, where are we? Here we go. That's actually measurable. And what's so cool about this is going to pave the way for us for next week. What do you see right there? What shape do you see? It's a bell curve. Very tight, but it's a bell curve. If you ignore this tail, which mathematically you can do because it shouldn't happen anyway. I say shouldn't happen statistically, not mathematically. It should happen, just not very often. You get these beautiful bell curves. When the sample sizes get big enough. We did not see this with ours. Did anybody run disc draw on our little flock of 4? You probably didn't. I'm going to do it again for you real quick. You can do it too if you want to for practice, but you already did. You might be bored of this. If we do our little flock of 4.
That was distill you did, not distill.
Oh, disc fill. I want to do disc fill. I meant disc draw. You have to do disc fill first because it's going to draw whatever's in disc fill, if that makes sense. Binomial, 0.9. Okay, there's our distribution done. But now what I'm going to do is I'm going to run that disc draw. That's what our distribution looks like. It's not big enough to pull a bell curve. There aren't enough data points. It looks like it's trying to. It's trying to, and then, because you haven't bought enough birds to see the other case yet. Remember, you have to buy, remember what Carly and Pat said, you've got to buy enough birds to see the roosters start to show up on average.
Now, if you put in 10 birds,
Let's put in 10 birds. I was hoping you would go there. Do 0 to 10, right? This is you bought 10 birds. On average, how many boys should you be getting?
1.
1! You should be getting 9 girls and 1. You guys have already discovered part of this lesson on your own. Thank you for being clever at 8:15 in the morning on a crappy weather day. Okay? 0 to 10, binomial, 0.9. Let it run. Do you want to go straight to the graph or do you want to look at the distribution first?
Go to the graph.
Straight to the graph? Yeah, just go to the distribution, we'll go to the graph first, we'll come back. Here's your disc draw. Notice what it's starting to do.
Go down.
It's starting to, it has to, because once you've bought 10, you've allowed, it's not long-term enough to be long-term or on average over time, but it's starting. It's starting. The likelihood, it's no longer likely that you got all girls. That's not the most likely, excuse me, let me rephrase, that's not the most likely outcome anymore. The most likely outcome is now 9 girls and 1 boy. Which makes perfect sense, doesn't it?
Yeah.
Because it's a 90% chance of a girl. That should be the most likely outcome. Go ahead.
Well, you were gonna say how the easy way to find the average.
You've already got it. You figured it out. Watch this. No programs. We can use the calculator, though, if you want to use the calculator. Suppose my student needs precision, mathematical precision. She buys 41 birds. And she needs to know to the nearest 10th place how many girls should be in that flock of 41. We know it's about 37, but she needs more precision than 37. She needs to know what, 37 point what, or 36 point what. Can you get, without running disc fill or disc draw, can you give her that average? 41 times 0.9. You guys discovered that last class, remember? Every time you add a bird, you add 0.9 more girls. Remember? 1 bird, 0.9 girls per bird. 2 birds, 1.8. 3, 2.7. 4, 3.6. Every bird added adds 0.9 more. 41, you can add 0.9 41 times. But good God, this is why we invented multiplication. So you don't have to. So you would simply say 0.9 times the 41. There, it's 36.9 girls to be exact. Be precise, not exact. 37 is plenty good enough. But that's how many girls you'd have on average. That's it, guy. You take however, whatever the maximum number is, the total number possible, times the probability of what's called success, that's your average. There's also a clever formula for your standard deviation, which is not at all intuitive. We'll get into that later. if you need it. You, of course, friends, you don't need the formulas necessarily if you have dist fill, because once you fill the distribution, what can you run? And always 1 bar stats. You can always run 1 bar stats to get it, and it'll pop it out for you.
But don't
But-
forget the L1L.
But don't forget the L1. Oh my God, please don't forget the L1. Otherwise, you're treating it as a uniform distribution, which is sometimes true, but not with chickens. Carly.
So, will your programs only go up to a certain population number?
The ones I have you do don't exceed its capability. I haven't found its limits yet. There are limits, definitely. Obviously, if we can limit it on a factorial, there are limits to what it can do. I don't have you guys go above 50, and 50 is well within its range. If you need more, I've got a video attached to a quiz that's going to come next week, or 2 weeks, the last week, that shows you how to do this stuff in Excel, if you need more computing power. I doubt you ever will, honestly. But not this class anyway. But if you take this out to use it anywhere else, you're going to want to use Excel or something like that. And I've got a video with a link to show you how to do it. Actually, I just got a comment from some person in Illinois saying, "Where'd you get the .487 from?" And I'm like, okay, that's not one of my students. I kind of clicked on her profile. My gosh, she's in Illinois. How did she find this? But I'm like, it's the binomial distribution, weighted average, blah, 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 blah. I'm starting to see that second C in COCC is becoming a much broader net. Central Oregon Community College now stretches as far as Illinois and France. Very, very cool. Anyway, for this class, for your assessments for this class, you get everything you need in the TI.
Okay.
Go.
So, aside from what we do in class, so it seems like as we go up in numbers, the probability of getting to that 90% keeps going up. So I'm wondering over time how high the population has to get.
Can you hold that question? You're about a day.
Okay.
I want to focus more. You've crossed over into what's called the normal distribution. When you let n go off to infinity, essentially. You want n to go as large as possible to achieve a certain goal. I want that too. But I want to make sure that we can keep it discrete for now and make sure we understand ins and outs of this really, really well before we take it n going off to infinity. If that's okay.
Yeah.
Can you stop it?
Say that again.
Can you stop it?
Can you stop?
And when you get to where
Oh, most of the times you have to. Like for example, Gallup. To bring up, I use them a lot just because they seem to be in the news a lot. Gallup does a poll. They don't survey infinitely many people. They'll survey 2,000 and say we are 95% confident in our results. Now the reason they do 2,000 is because they have this tool. They don't call it distfill, I didn't write their program, but they have the binomial distribution. And if they survey 2,000 people, that means their smallest is 0 and their biggest is 2,000, and then they can fill that second column with that. That's good enough for 95% confidence. You want even higher. It sounds like you want even higher. Carly, what do you go even higher than 95?
No, I just was wondering, I was just looking at the probability of getting exactly 90%.
Which you can't always get to exactly. That's your point. You can't always add up to exactly 90. Is that what's concerning you?
No, I'm just wondering what happens to that probability over time.
Oh,
Like in this-
yeah, then
the
please
40
definitely
months.
hold that question if you don't mind. That's a fantastic question. You're bridging, I'm envisioning an image in my head of the binomial and the next step and this beautiful arrow that you're painting for us. But I don't want to leave the binomial behind before. I want to make sure that everybody's 100% solid with it first, if that's okay. Great question. You don't have to go that close to infinity, but you do have to get larger than the small sample sets we're dealing with. Thank you for that.
Okay, now back to like the 0.9 on these
Yes.
on your chickens, right?
Yes.
Okay, so Joe behind the counter says, Sean, it's 0.9.
0.9.
So you got to go with what he says
Exactly.
because you don't have the historic looking in the chicken things, vents or whatever to be able to tell like, okay, there's that 90%. So you got to have that number.
That is one of what's called a parameter of the binomial. There are 2 parameters of the binomial distribution. One of them is that probability. You're done without that probability. And the other is?
The range?
The range, that high number of the range. It starts at 0 always and goes up to the max. So you need to know n, it's usually called little n, and little p. Now you notice we were also using that 0.1 in class last time around, but that's a consequence of the 90%. It's whatever's left over. So you need 2 parameters. Right, here's why I wouldn't let my wife buy, I wouldn't let my wife buy the chickens from the middle school, or from, not buy, but take. They're gonna raise chicks at school on a ridge. And well, she's like, well, why don't we just get them from them? I'm like, okay, well, here's the problem with that. If we do that, we now have a 50% chance of a girl. Assuming that sex is basically distributed like it is in humans, you're gonna have half boys and half girls on those eggs. So what is that curve going to look like? What's that curve going to look like? If it's 50% likely that we get What is that gonna look like? I gotta vote for uniform, I gotta vote for bell-shaped. Alright, I just ran it, you guys can too. You guys can run your binomial at 0.5 between 0 and 4. Go ahead. You know what the most likely outcome is in this case, don't you? What's the most likely outcome if you get 4 eggs or 4 chicks? And 2 and 2 is now the most likely outcome because half of them should be girls, 0.5. Does that make sense? You should have 2 and 2 is now the most likely, so you're going to be expecting 2 roosters on average. Check it out. Let's take a look at it. There's Robin's bell curve. Now, here's the chance. There's the chance of getting no girls at all. 6%. That's too high to make me happy. Right? That's too high to make, that's all roosters. No girls, all roosters. Unfortunately, that's also the chance of all girls because it's the same probability. So I got too high odds for all roosters and nowhere near high enough for all girls. I'm like, this sucks. There's your mode. 3/8 of the time. 3/8 of the time. FYI, if anybody did the quiz for this week, this is the same distribution you did Montague Way to Connect. If you did the quiz on the betting with your friend, the $, this is the distribution for that quiz. FYI. I'm a bastard like that sometimes. Yeah. Total bastard. Sometimes yeah. But this is why we don't do that. We have to know that probability, right? We have to know it. And the way he cavalierly said 0.9 made me wonder. I'm like, where did you get that number from? But I've heard that number repeated over and over again by folks. So that's all I can use. It's the best I can do. I can do ranges of values and feel better about it. What if it's as low as 0.85 or as high as 0.95? Then I get a worst case scenario. And that's what's called in engineering lingo, that's what's called lower confidence bound and upper confidence bound. Go low, go high, assume the truth is somewhere in the middle. Drumhead manufacturing, drumstick manufacturing, exactly the same way. Build it for the worst scenario and overbuild it for that. That way chances are you'll have it covered. Bridges are built this way, for Lord's sake. Yeah? So Pat, yes, 2 parameters, sample size and probability, and you can see how it vastly changes. You could also, if you, oh, Joe, go ahead.
Could you get a more accurate percentage if you took how many chickens you bought from that one person, and then, you know...
Assuming I've got enough of them, yes. Joe's got a good point. This is how I'm teaching my 105 classes more and more, even more than you guys. Collect data to get the probabilities. Keep collecting, collect. We did the Monty Hall question yesterday with the doors. And instead of having just one kid play each time, one kid played for a lollipop. But the entire class bet as well. So I got 20 times more data. And it went right to the result 20 times faster. So yes, the answer to that is yes, as long as you can get A, enough data, and B, good data. That's the trick too, is knowing your data is good. I learned some good tricks yesterday at 105 for that. Yeah.
But it's not just numbers,
no.
Right? It's like you know, you got to think about where like the technical and tactical proficiency of like you're gonna be like, okay, here's the middle school, we're raising chicks, like nobody's looking in chicken butts, as opposed to they came from
chicken butts.
As they came from a a breeder or whatever.
Yes, totally. Where did they? That's unfortunately, you could get that obviously, right? You could back check that and figure out where all that stuff came from and figure it out. Yeah, but that's why I keep putting pause on these awesome questions because you guys are actually heading towards 244 questions. Bless you both for that. Bless all of you for that actually. But I want to focus on the mechanics of the binomial and strip it down to just the mathematics right now, if that's okay. I'm going to show you some connections to where we're going with it, obviously as well. But yes, the answer to that is a big fat yes, absolutely. The trick is we can get bogged down in that and never actually move forward with the binomial itself because we never get past the data collection part of it. And 244 has this problem every day. I don't agree with this study. I didn't say you had to. I'm saying here's some data to play with. You know, I mean, like, let's play with the data, let's get the mechanics, and when you take your research methods classes at OSU, that's all you'll talk about. Anybody taking that class yet, research methods? Some of you may have to at some point. That's all you do is talk about how to get good data. Now you'll have the tools to deal with it, and then you get the good data. It's much better to learn it in this order, I think, than to learn it in the other order. Please.
I have a question
about
this.
Yes.
So when you say the highest likelihood is 0.375, do I multiply that by 4 to say 1?
On average. On average. Exactly. But the trick is not that probability there. The probability we started with. If you multiply that probability by 4, what are you multiplying there? You're multiplying the probability of 2 girls with the number 4. And that doesn't make a whole lot of sense. You got a mismatch there. So how many chicks were we getting from the school?
4.
On average, how many should be girls as a percentage? Half. 0.5 times 4. On average, you're going to get 2. So what you're seeing is, you're seeing the average with the most likely probability.
Oh, okay.
That's not the probability of one girl. That's the chance of getting 2 girls and 2 boys, which is the most likely
Oh, okay.
possibility.
Gotcha.
Is that fair? It's believable, not fair. Believable, hopefully believable. You don't, the only time you ever multiply these individual probabilities by anything, as you noticed if you did the quiz yesterday, or today, is when you multiply them by this to get the average. So that times that, plus that times that, plus that times that, plus that times that, plus that times that, all added together is the average. But for the binomial, the average is just 0.5 times 4. Now the reason, some of you are thinking, why the hell didn't you teach us this times this is the average 5 weeks ago? There's a very good answer for that. It only works here. It only works on binomial distributions. That's why. It doesn't work anywhere else. It only works for these kinds of, now fortunately these are everywhere in your life, fortunately, but it's not everything that's in your life. They're every Gallup poll, every Quinnipiac poll, everything you read in a journal generally is based on this. But there are other things, like the single die rolls, like life insurance policies, that aren't governed by the binomial. So it's better to have the overriding tool of how to do an average than just give you a special case. Does that make sense? I'd rather teach you how to use a record player, which is the thing that plays records, than give you Cindy Lauper and say, this is the only record you can play on this weird machine over here with a needle. Give them a fish, give them one a fish, versus teaching them how to fish. Carl, you had a question, I think. So my hand went up somewhere. Oh, please, Robin.
Can you just remind me what binomial distribution is?
We haven't even formally defined it. Let's take our 5 and come back and do that. Yes, we've got the cart way in front of the horse. We've got the cart way in front of the, let's come back to that. I've got a nice slide hopefully it'll work through all that.
Okay.
Cool, take 5. I actually have to run on the side.
I guess.